Okay, so today we want to talk about improper integrals. Yesterday, I think we might have one more thing to do. Let me take a look on approximations. No, we did some error formulas. I guess we didn't do the midpoint error bound. Does anyone want to see that? How do you guys feel about those? I don't want to spend too much time on it. It looks like there's one homer problem on it. You can imagine there's going to be one, maybe two. What midpoint? Well, if you were in lecture yesterday, it's the midpoint of the intervals from the partition. You're essentially just using the midpoint value, the midpoint x value. Yeah. And then use that for your f values. So we kind of went over how to do the tables, how to compute the sums. It's very algorithmic. The challenge for you guys, or at least the practice you guys should do right now, is kind of going back and forth between the sort of abstract notation, the sum notation, and then the actual algorithm. Being able to formalize algorithms into mathematical notations, really important. That's actually one of the lackings I've noticed about computer science students. Sometimes they get deep into the computer science and some of the broader pictures of math they don't quite understand. Whereas if you understand the math, learning the computer science, not too hard. You just do the computer science and then you can formalize the computer science from the math. The only thing we didn't do, we did an error bound estimation. So if we want to be within a certain degree of accuracy, right? Remember those words, that phrase, within a number, within 0.0001 is what we had. That is an error. So we simply take our error formula, or the max error formula, and set it to be less than or equal to that, and then solve for our n, the number of partitions. So we saw one with the trapezoidal rule. I don't really want to do one with the midpoint rule, but we can if you guys want to review it, because it's exactly the same process. The only difference is that the error bound for the midpoint rule has a 24 in the denominator instead of a 12. So you're going to get a much quicker or much smaller degree of accuracy. Okay, so let's go ahead and continue then with improper integrals. And improper integrals are basically going to be integrals to infinity, or integrals over asymptotes. So we'll do this in two parts. Let's take a look at integrals to infinity. And what we want to do is let's compare the integral from 1 to infinity of 1 over x versus the integral from 1 to infinity of 1 over x squared dx. So graphically, it's going to be hard to tell the difference, and especially if we're just graphing by hand. 1 over x looks something like this, and 1 over x squared decays a little bit faster, so it's just tighter. Ugh, hand is slipping. It's just tighter in terms of the axes. And we're, of course, integrating from 1 to infinity. And so our question is, well, our integral still has the same interpretation. It is the area under the curve. But our problem is, of course, we're going all the way off to infinity. How do we add up an infinite length is our question. And this is a question we're going to be exploring a lot this semester. It's, can I add up an infinite number of values? So of course, with these improper integrals, we could do Riemann sums. And we could do something like an upper bound, use orange here. And if I take boxes that are slightly bigger, so if we use like a left-hand rule, we have all of these boxes, and now I'm just going to be adding up the area of the boxes, and we could choose a nice delta x, say delta x equals 1. So in some sense, all we're going to be doing is adding up all of these y values. Can we add them up to get a finite number is our question. In particular, with the integrals, the other way we want to ask about it is there a finite area under the curve even if it extends to infinity? And I guess to be specific, let's say even if the x values, even if the x's extend to infinity. Well, in Calc 1, we studied a few things. Calc 1 is all the study about rates of change. I like to kind of make a point that Calc 1, in some sense, is a study of infinity, especially once you get to L'Hopital's rule. It's a study of how we can get to infinity. Functional growth is a big part of Calc 1. You learn polynomial growth, you learn exponential growth, and you learn, hopefully, factorials. We'll introduce, I don't know if your Calc 1 instructor mentioned factorials. We'll talk about factorials this semester. And then other functions, even higher rate of growth, functions like x to the x. And then when we're taking limits to infinity, we're often comparing which one goes to infinity faster, so to speak, or do they go to infinity at the same rate relative to some constant? The converse of that is decay, is when functions decay to 0. So in this context, really what we're asking, is there a finite area under the curve? Another way we want to talk about this question is, do the functions say does either function decay fast enough to give finite area? So these are the questions we're going to explore. So those are our concepts. Computationally, it's actually not too bad. So simply take a limit of the integrand. The fundamental theorem of calculus is still going to hold. So when we're doing an integral from 1 to infinity of 1 over x, what we mean by that is to compute the integral for some finite value bigger than 1. And then take the limit as that upper bound goes off to infinity. And easily enough, we know these integrals. Oh, I'm sorry, natural log of x. And of course, natural log of 1 is 0. And now what happens when we take the limit as t goes to infinity of natural log?
Is it infinity?
Infinity. Infinity, sometimes I think, I don't know if WebAssign likes undefined. Sometimes we call it
on WebAssign. You type in D&E, does not exist.
I don't like that. D&E does not exist is not a good. I want to start differentiating between does not exist and undefined or infinity. Let's call it infinity, and I want you guys to start using infinities. You'll have to change whatever formalities you have to use for WebAssign, because there's a big difference between a limit not existing. So, for example, if you have sine of x, what's the limit as x goes to infinity for sine of x? Does not exist. Sine of x oscillates between two values, and we'll see a lot of sequences and series that do that same thing. The limit just doesn't even exist. Whereas if the limit keeps getting bigger and bigger and bigger, that is what we define as infinity. So infinity is a better mathematical description of what this limit is. Okay, let's take a look at 1 over x squared. We do the integral again. And I put infinity there. We're going to put our dummy variable t. We do the integral. 1 over x squared is going to be minus 1 over x integrated. So we'll get the limit as t goes to infinity of negative 1 over t minus a negative 1. And now, as we get off to infinity, we'll see that our limit is 1. So we see that both things can happen. Sometimes we get a finite value. Sometimes we get infinite value. So our definition. So for any improper integral, there's two types, and it doesn't matter which type, whether it's an integral to infinity or an integral over asymptotes. We'll see examples of both. For any improper integral, if the limit is finite, we say it converges. if the limit is infinite or does not exist, then we say it diverges. So converging and diverging, we'll be using those terms quite a bit this semester.
So I have a quick question.
Yeah.
So is it actually exactly 1, the area of the graph?
Yep. Yeah. Crazy, right? If we go back
Yeah,
to
that doesn't really make sense intuitively, but I guess.
no, it doesn't. Well, let's take a look. Let's do a little numerical calculation. So our integral started here at 1. So this was 1 over x squared. If I plug in that 1, well, where does it intersect the graph? Here at 1. Right? What's this value? So 2. This value here, what's our y value at 2?
1/4.
1/4, right? So the graph is a little misleading the way I drew it because this value should probably be lower visually. So you can kind of think, well, if we were doing an over approximation, if we were doing these left-hand sums, what's the area of that first box? Area of the first box is 1. That's literally what we just computed as the entire area under that curve. However, if we were to do a right-hand approximation, the area of this box is just 1/4, which is grossly under. So,
Dr. Belcher, but that graph, like the arrow never ends. It never ends up reaching its asymptote. So like it goes on indefinitely. So I'm confused how you can actually compute the area under the curve to be like finite at 1.
Well, it's like as it gets infinitely large, the number under the graph is getting like infinitely smaller as it goes on. So although it sort of never terminates, you can never take away enough, or you can never add enough area that's under the graph in order to get past 1.
Yeah. Yeah. So some of you guys have had Calc 2 before. You've seen infinite sums in series. It's a little weird at first. I mean, let's diverge for a second before doing some more examples and talk about just kind of theoretically what's going on. I think it's called, oh, I forget the guy's name. Oh, some sort of paradox named after a guy.
Is it like Xenon or something?
Zeno's paradox. Thank you.
Yeah, something like that.
It has to do with Zeno's paradox. So how can we get anywhere? How can you walk across a room?
Is this like the ant on the string type thing? If you keep pulling the string, or like
this is if we keep walking halfway. So let's say we need to walk. Let's say I don't know 1 mile. Let's say this whole length is 1 mile. Well, in order to walk 1 mile, I have to first walk half a mile. Right? And then the remaining half a mile, well, I would have to walk half of that before getting to the end. I'd have to walk the 1/4 mile. And then once I'm here to get to the end point, well, I'd have to cross the halfway point. We'd have to walk 1/8 of a mile, et cetera, et cetera. So what's happening? We have to walk 1/2 plus 1/4 plus 1/8. The next one's going to be 1/16. And if we keep doing this, I could keep dividing the interval in half more and more and more. And ultimately what we would get is a sum of values that are progressively getting smaller, right? And they're getting smaller at a pretty fast rate. Each value that we have to add, each value that I have to cross is halfway the distance to the goal. So it's halfway the previous distance I just walked. But yet there's an infinite number of terms here, an infinite number of numbers. So the question is, well, how can I add up an infinite number of numbers? Well, and our answer is yes. Because what's the total distance we walked? 1 mile. And so the idea is that the numbers, let's say the consecutive numbers, are decaying or decreasing fast enough so that the infinite sum is finite. And in terms of rate of decay, we might describe this function as something like 1/2 to the x. And all we're doing is taking maybe a left-hand Riemann sum starting with x equals 1. When x equals 1, x equals 2, 3, 4. And so this is going to tie into later in this lecture when we talk about comparison sequences as well. This is kind of what I was prefacing everything with: rates of growth and rates of decay. Hopefully you guys learned a lot in Calc 1. We'll be exploring that again in Calc 2 terms, because we're going to be comparing now rates of growth, rates of decay, and can we add up infinite number of terms? Can we integrate over an infinite length? And this is what's going on with our x and x squared. And it's counterintuitive at first, right? Because the graphs look pretty similar. And this one, the idea is, well, this one's, it's decaying to infinity, but you know, out here, every number I'm adding on, you know, every unit interval that we go, the area we add is getting smaller and smaller. Same thing out here. Areas we're adding are getting really, really tiny. You know, you can kind of think about it, well, if we walked that mile, well, if you walked, you know, a 1 more millimeter, would anyone really notice the difference? Or you can kind of ask, well, if I walked just shy of it and if we keep only walking halfway there, and the distances we have remaining are so tiny, is there an upper bound to the maximum distance we can cover in walking this type of pacing, right? Walking halfway and then halfway the remainder distance. You can ask, is there an upper bound to how far we can get based on the numbers we're going to keep adding? And so this is what we now need to explore. So our big question, well, one of our x we saw actually diverged, even though the function it decayed and it was approaching its asymptote but never touched its asymptote. But with 1/x, even though we're adding up tinier and tinier areas, those tiny and tiny areas are big enough that the total area ended up being infinity. But 1/x squared, it turns out that the total area under that curve was 1. So our question is, what type of functions decay fast enough so that the integral from whatever constant, whatever starting point out to infinity makes this interval converge. So this is what basically this entire section is about. So we're studying rates of decay, which are the inverse of rates of growth. And now how can we add up areas and get finite areas over an infinite length? So the first thing we're going to explore, since we saw 1 over x diverged, 1 over x squared converged, first thing we want to do is our p-test, or our p-test formula. And we want to know for what values of p does the integral converge. So we're going to integrate from a to infinity of 1 over x to the p. So we know x and polynomials, x to the p, those go off to infinity at infinity. So of course the reciprocal, 1 over x to the p, is going to go off to 0. And yeah, no, let's keep it like that. I think we're going to want p at least bigger than 0. Let's specify that. Of course, if p is less than 0, that would imply a reciprocal, which we don't want to do. We want functions to decay. And then our a value, we should probably also specify is bigger than 0. Of course, there is an asymptote at 0. And we'll have to learn to deal with that as well. So we'll do the integral. So for p not equal to 1, what do we get? The integral from a to infinity of 1 over x to the p. I'm going to take some shortcuts with all the notation and work because, to be honest, writing the limits, it's kind of pointless, and you'll see why. What's going to happen when we integrate that? We will have, so x to the minus p. So we'll have x to the minus p plus 1 divided by minus p plus 1. And we want to evaluate it from a to infinity. My understanding or my belief is that if we write infinities here, there's no reason we shouldn't be able to write infinities here and understand that that infinity means when we plug that in, we're taking the limit. And let me change this statement here. So for p not equal to 1, let's say specifically, let's break it down into subcases since you guys are engineers. So now we have this case, and now we're going to do for p strictly greater than 1. When we plug in infinity, so if p is bigger than 1, that means that this term is negative, right? We can write it as 1 over x to the 1 minus p. Did I do that right? Sorry, minus 1 plus p. I did not even change the signs. Little brain fart there. So multiply by a negative. And then now P is bigger than 1, so this exponent is positive. It's in the denominator, which means when I plug in infinity, what's going to happen? It'll decay to 0. So we'll have 0 minus 1 over A, and I'll switch those back to the P minus 1. And let's write it all out, I suppose. Minus 1 over P plus 1 times 1 over A to the P minus 1. And A is a finite value bigger than 0. So finite converges. So we're good when P is strictly bigger than 1. For P less than 1, the integral is the same, or at least up to here, right? So we had 1 over minus P plus 1 times 1 over x to the P minus 1. Sorry, let me rewrite that. We had 1 over minus P plus 1. In this case, let's keep x in the numerator. So let's go back to that one, is where I wanted to go. X to the minus P plus 1 from A to infinity. Why did I want to keep x in the numerator in this case? Because P is strictly less than 1. So P could be a fraction, x to the 1/2, x to the 1/3, somewhere between 0 and 1. And of course, negative P plus 1 then means that this exponent is positive. And so what's going to happen now when we take the limit as it goes to infinity? If we plugged in infinity here, we would have infinity to a positive constant. It'll give us infinity minus whatever number we plug in for A, and which is still going to be infinity. Diverges. So fractions like x squared, or excuse me, fractions like x to the 1/2, compare that with something like x squared. So x squared grows really fast, goes off to infinity, right? Parabola. X to the 1/2 square root, right? You know, everyone hopefully knows the shape of the graph. It goes off to infinity, but it's concave down. And so what's going to happen when I take those reciprocals, anything that goes to infinity really fast, when I take 1 divided by that, it's going to go to 0 really fast. Whereas things that go to infinity really slowly, like x to the 1/2, when I take the reciprocal, 1 divided by x to the 1/2, it's going to decay slowly as well. And since it decays slowly, it doesn't decay fast enough. The numbers underneath the curve for 1 over x to the 1/2, the area under that curve is actually going to be infinite. Of course, our last case, we've done. That was the first example we did. Of course, we'll get natural log. It's going to be a different integral there. But as we already saw, even if we change that starting value to A, the limit as t goes to infinity is going to be infinity. So this is a rule. You guys can quote it, use it. You don't have to recompute these integrals on homeworks. So the integral from a to infinity of 1 over x to the p dx for p bigger than 0, a bigger than 0, converges for p bigger than 1, diverges for, I guess we shouldn't have equal to 0. It wouldn't be wrong, for p between 0 and equal to 1. This is our p-test. So not all the functions are going to be p-tests. You kind of have to remember how to do your limits. Let's see a couple other examples. Of course, we can first order, we always want to try to compute them by hand. Eventually, we want to get into comparison tests, which we'll talk about at the end of this section. So let's just do a couple more examples real quick. Let's say we have something like an integral from minus infinity to 0 of x e to the x. First thing, why is this improper? As we can imagine, integrals to minus infinity are the same thing as integrals to infinity, just flipped over the y-axis. So of course, negative infinity is treated very similar to positive infinity. And if we wanted to, we could even just pull a minus sign out and flip the bounds. We can still do that with the infinities. So of course it's improper. We're integrating to infinity. We've got to go through our integration techniques. I'm just going to use the original function and keep the limits with the negative infinity. We have a product and there's not going to be a good u sub. So we're going to want to use integration by parts, which hopefully everyone's getting good at by now. And so we will have x e to the x minus the integral from minus infinity to 0 of e to the x dx, which is just going to be x e to the x minus e to the x. Now we need to evaluate from minus infinity to 0. And nicely enough, what's going to happen when we plug in 0? We get 0 times e to the 0 is 0, minus 1, minus, and now what's going to happen when we plug in negative infinity? This term we've got to be careful about. This term's fairly straightforward. Let's do the formal process. This would be the limit as t goes to infinity of t e to the t goes to negative infinity, excuse me, t e to the t minus limits we can split over a sum. This term's finite. It's just going to hang out in our work. And then this term here, what's going to happen here? E to the negative infinity is going to be 0. So the only one in question is this guy, and we have to figure out what's going on here. I'll give you a hint. It's 0. Do L'Hopital's rule. Check that. You guys should all be pretty good with the L'Hopital's rule by now. And if your Calc 1 instructor was astute enough to teach you guys that what's happening with e to the t, exponential growth, right? Exponential growth. And if we're going to negative infinity, it's exponential decay, like radioactive decay. Exponential growth and exponential decay are both really fast rates of growth, rates of decay, respectively. Whereas this one's a polynomial. Polynomial growth pales in comparison to exponential growth. So exponential growth will always dominate. And so if this is going to negative infinity, even though we'll have infinity times 0, do L'Hopital's rule, do the fancy tricks with that, you should see that the exponential function will always dominate. So this one will go to 0 faster than t goes to infinity, and it will dominate and bring the entire limit to 0. So check that on your own with L'Hopital's rule to confirm. That's the bigger picture idea of what's going on with rate of growths of these functions.
Dr. Belcher, is there any chance you can go back one page and go to the top right above where it says for what values of p does the interval converge? I just missed the line that you had right above that. Okay, awesome. Thank you.
Yep. Okay, let's do one more example, then let's jump into these other types of discontinuities. Asymptotic rate of growth. Asymptotic rate of growth is the only rate of growth that essentially is faster than everything. If you're just looking at limits to infinity, it's going to be like fractional rate of growth, or excuse me, logarithmic is always the slowest. Logs go to infinity, but really, really slow. Then fractional exponents, x to the 1/2, x to the 2/3, specifically exponents less than 1. Then polynomial rate of growth, next fastest. Maybe we should write this down. Let's write this down. This will come in handy when we get to sequences in series. So rates of growth to infinity in order. Logs for specifically not like fractional bases. Fractional bases are weird. Then fractional exponents. Specifically less than 1. Then polynomials. Or you could even call it, you can even have fractions if you want to use x to the 5/2. Still going to go to infinity. The next functions are going to be exponentials. After that, it's going to be factorials. And don't worry if you don't know what this means. And it has to be an integer. We can't extend a factorial rate of growth to make it continuous. But don't worry if you don't know what that means at the moment. We'll cover it in sequences and series. It's an interesting concept. It comes up a lot in combinatorics, but it lies just above exponentials, but below something like x to the x, where now we have not only an increasing exponent, but an increasing base. So this one goes to infinity really, really fast, really fast, really fast, fast, not very fast, really slow. The only thing that goes faster than this are asymptotes. We'll get to that. So let's talk about, let's do one more example of integrals to infinity. wanted to just go through this process and see all the different functions we have. We've done polynomials, p-tests. You've seen an example with exponentials, and the exponentials are going to be very similar. You should expect that if the exponential, or we have exponential decay, almost always converges out to infinity. I'll leave you guys to play around with that with the exercises you see. Other things we might see are going to be things like minus infinity to infinity of 1 over x plus 1 over 1 plus x squared. So you guys should recognize this. This is just kind of going to be a quick example. Well, why should this grow, or why should this be finite? Let's start talking about this. You want to think of things in terms of their order of growth, and also think now if any of these are in the denominator, that's the rate of decay in the same order, right? 1 divided by this is going to decay to 0 really fast. 1 over an exponential, or an exponential to a negative exponent, right, is what that means. Going to decay really fast. And we already saw that 1 over x squared ends up being finite. And now the denominator here is the denominator bigger or smaller than 1 over x squared?
Bigger.
Bigger.
Oh, wait, sorry. Yeah, bigger.
Yeah, denominator is bigger, which makes the overall fraction smaller. So just be careful with that line of thinking. It's easy to get that mixed up in your brain. The overall fraction is smaller than 1 over x squared. So if 1 over x squared ends up being finite, and this one overall is a smaller function, meaning it's going to decay, it's going to be underneath our 1 over x squared, then it should also converge.
Can't you just look at it as the polynomial is the most important thing, basically? It's the most significant.
In some sense.
The squared term is the most significant when you're going to a limit than the
pretty much
constant.
Yeah, the highest power specifically. That's called the limit comparison test. We'll be talking about these a lot this semester, both comparison and limit comparison tests and how they come up. So to just do this one quickly, what's the antiderivative of this? You can do a trig sub if you like. We've got a sum of squares, so you can make x equal to tan theta if you'd like. When you go through it, you would end up back solving and you would find arctan x. Of course, the derivative of arctan, you can also remember from Calc 1, is 1 over x squared, 1 over 1 plus x squared. We got to plug in our limits from infinity to negative infinity. And you just have to remember, what's the limit as arctan goes to infinity?
Pi over 2.
Pi over 2.
Yeah, good. Hopefully all you guys got this now. It came up on the homework, I think. So it'll be pi over 2 minus, what's the limit as arctan goes to negative infinity?
Negative pi over 2.
Negative pi over 2. Nice. And so we just get pi. It's a finite limit there as well. Okay, let's get back to where I was kind of jumping around. In terms of rates of growth, the only thing that would be faster than these would be what's called asymptotic. Why asymptotic? Well, asymptotes go off to infinity in a finite interval. Yeah, let's split some of this up. Other than doing more compositions as well, like we could take x to the x to the x and keep going. But in terms of sort of mathematical concepts that are introduced, that's basically it. You could always compose functions and take functions of functions to get even faster rates of growth. But the only sort of newer concept that's sort of different from what's introduced is asymptotes. Why asymptotes? Because there they go off to infinity in finite time. right? If we have a function, something like 1 over 1 minus x squared, let's say 1 over 1 minus x quantity squared, what's going to happen when x is equal to 1? It's going to go off to infinity, right? And so one of the questions, let's actually go back to our standard question that we started with. With 1 over x to the p goes off to infinity at 0, and of course decays to 0 as x goes to infinity. Let's change our bounds. Let's put our 1 actually here. Let's make it an a. Let's keep it a generic constant. And now what we want to know, well, what about this area? We saw in these first cases, as functions decay to 0, they're asymptotic to 0, we can have finite areas. Well, what if a function is asymptotic on a vertical asymptote? So our question is now, once again, for what values of p? Specifically p bigger than 0. And then for a bigger than 0, does the integral converge? And now what is our integral? Well, we're not integrating off to infinity. We're integrating from 0 to a. So integrals of this type, I think the book calls them type 2 improper integrals. I would call it asymptotic. Asymptotically improper. I don't know if there's WebAssign topics for this for you guys. I know in the math department, some of the WebAssign for this, they have you like identify why is the function improper or why is the integral improper. So you either have to say function is proper, it's fine, or you would say something like the function is improper because one of the limits is infinity, or it's improper because the function is asymptotic. The function goes to infinity. Within the intervals specified. Usually the asymptote is at one of the endpoints, but it doesn't have to be. So for example, we could have this function here, 1 over 1 minus x quantity squared. We could have an integral on both sides of the asymptote where we have to add up both areas. So sometimes identifying these improper integrals that are asymptotic, got to be careful because it's not as simple as checking the bounds always. But a lot of the cases are cooked up like that, where the bound, one of the bounds is the divergent point. So how do we do this? Same way, since it's divergent at infinity, right? The function doesn't exist. Excuse me, divergent at 0. The function does not exist at 0, or it diverges to infinity at 0. We want to compute the integral and then compute it as a limit. So we've already seen how to do this one. To formally write it out. And specifically, we could take 0, going from 0 to the right. Since the asymptote is at 0 and we're integrating to the right, sorry, that's an A, and our A was positive. Since we are going from 0 to a positive value, we're computing the positive side of 0. Man, I'm changing variables already. Sorry, X's there on those guys. We do the integral and compute the limits. So let's see what we get. We've seen the case for p equals 1. We get limit as t goes to 0. In these cases, this, might be good practice to include the limits in these cases, just so you're not, sometimes you can be a little callous when you plug in the zeros or the limit and, make an arithmetic error. But just as well, if you're paying attention, writing the limit isn't terribly important in my book, as long as you understand that that's really what you're doing. Okay, so we had p equals 1. We're taking the limit as t equals 0 of natural log of x when we integrate. And of course, we're going to have t to a. And so what are we going to get? Natural log of a minus natural log of t. And the limit as that goes to 0. What is natural log of 0?
Negative infinity.
1.
Negative infinity. Yeah, be careful. That's big. Another big point to emphasize in Calc 1. Natural log of 0 is negative infinity. Natural log of 1 is 0. Natural log of e is 1. So this will be divergent. For p bigger than 1, when we do the integral, we will have 1 over minus p plus 1, x to the minus p plus 1, t to a. We plug those in, and what's going to happen? We will have, let's write it as 1 over a to the p minus 1 minus 1 over t to the p minus 1 p is bigger than 1, so these exponents are positive. And now what's going to happen if I plug in a 0 for t? 1 over 0 gives us infinity. So it diverges. P less than 1, we will have the limit as t goes to 0 of 1 over p plus 1 minus p plus 1. We will have, let's keep x's in the numerator from here. So we will have a to the minus p plus 1 or 1 minus p, minus t to the 1 minus p. And now in this case, p is less than 1, which means what's going on with this exponent here? It's positive. P could be a half, a third, 2/3. And when I plug in 0 now, it's just going to be 0 to the 1/2. And so what are we going to get? 1 over 1 minus p times a to the 1 minus p, and of course minus 0. So in this case, we converge. All right, let's summarize that. Our p-test. So for p bigger than 0, a bigger than 0, let's see, the integral have the following properties. So for p between 0 and 1, our integral from a to infinity of 1 over x to the p diverges, but the integral from 0 to a of 1 over x to the p, we just saw, converges. So in some sense, even though if p is less than 1, right, x to the 1/2, 1 over x to the 1/2, decays really slow. So it's going to diverge off to infinity. However, it increases along the y-axis, along the asymptote. It approaches that asymptote much more rapidly. So this integral is going to converge. For p equals 1, both diverge. And then lastly, p bigger than 1. It'll converge when we integrate out to infinity. And it will diverge. Whoop, I gotta switch those at 0 to a when we integrate to the asymptote.
Can you just repeat your explanation of what's going on with like when in like when from 0 is less than p is less than 1 when that diverges but the other converges. Can you just kind of conceptually explain that again real quick?
Sure. Let's draw a picture. So we've got x and x to the 1/2. Looks like that. Looks like that. All right, this one will surpass it. Right, if we were to draw those on the same graph, the x would keep going. X squared, you know, it's going to keep going bigger and bigger, but it's concave down. Which means that if I take the reciprocal, what's going to happen, at least out at infinity, is because this is getting bigger faster, the denominator is getting bigger. So that means this is decaying. Oops, I cannot draw today. It's decaying much quicker than this guy. This guy's staying above the asymptote longer, or further away from the asymptote longer is what we should say. But now we got to think of what's going on closer to the asymptote. So closer to the asymptote, what's going to happen as I put fractions in for x? It's going to grow, right? If I have like 1/2 in for x, it'll be 2. At 1/4, we'll be up at 4. So in some sense, you kind of almost have to like turn them sideways or take the inverse function to really understand what's going on with these. On the other hand, what's going on with this guy, if I plug in 1/2, it's going to be square root of 1/2. So what is square root of 1/2? It's going to be a hard number to compute. And since we're taking a reciprocal twice, it's going to be like square root of 2. And so what's going on with these fractional exponents? What's going to happen is that it's going to sort of decay faster towards the x-axis. And then on the other hand, like the y values here, it's almost like the y values are getting big and too big for these sort of fractions that we keep partitioning into. So it's going to diverge. Whereas here, the y values are really small that we're kind of adding up for each of those partitions. And we can keep getting narrower and narrower, and it doesn't quite grow as fast. So in other words, the y values aren't growing too fast when the x values are shrinking really fast. So the x values can shrink really close to 0, and the y values don't jump up too high, which is what makes that finite. Does that make better sense?
Yeah, thank you.
Okay, so in the last 10 minutes of lecture or so, let's introduce comparison tests and hopefully see a few examples and at least write those down. You can always pick up at that again tomorrow if you guys want to see a few more examples. Compare tests is fairly easy. So suppose we have two functions, f of x, g of x are functions with that are positive and g of x is always bigger than f of x on whatever interval, I guess whatever starting point we care about, but on an infinite interval with a finite starting value. Then if the integral from a to infinity of f of x dx. So if f of x diverges, meaning it has an infinite sum, then g of x also diverges. If the integral of a to infinity of g of x converges, then the integral of f also converges. The integral of g is finite. It decays fast enough. And now I have a function that is smaller, still positive, so it's not going to go off to negative infinity or anything like that. And this one's going to decay faster, so it will also converge. So just pay attention to the order here. Let me do some highlighting and underlining. So our F's are blue, our G's we can make green. So what does that mean? What if F converges? Do we know anything about G? No. Right? It has to be in this order. So our logical implication goes that way, right? G of x converging implies f of x converging. If we only know that f of x converges, well, it's the smaller function. The bigger function could get a lot bigger. So we don't know anything about it a priori, unless we have more information about the function. Examples. So state whether converge or diverge, and why. So I have an integral of 1 to infinity of 1 over x plus x squared. So keep your inequalities correct. We are from 1 to infinity. You can write out things like x plus x squared is smaller than, bigger. And I'm already writing my inequalities backwards. It's bigger than x squared, which means if I take the reciprocal, the inequality flips. This denominator is bigger than this one, at least on 1 to infinity. Which means that this integral since the functions are positive, right, all the values we would plug into that function would make that function positive. We know it's bigger than 0. And we also know that it has to be less than this integral, x squared. And we know that this guy converges. So we're comparing our function to a bigger or smaller function and then determining convergence based off of that. So the practice here is, one, you got to practice using comparisons, comparing functions. So to bring up that rate of growth list again, You always want to compare functions either of like rate of growth or of one order above or below, often comes up. Here we see polynomials and polynomials in the denominator where we are integrating off to infinity. And so you want to compare with a function usually of the highest power, the highest degree will often dictate what's going on. Let's check some other ones. Let's do the integral from, let's say, pi over 2 to infinity of sine squared x over x. So what's going to happen with this one? So I've been putting the scratch work over off to the side. Sometimes it's helpful to deal with, you know, polynomials and then the reciprocals. Sometimes it's helpful to deal with the parts of functions. So I know that sine squared of x it's always between 1. So here we take out a part of the function. If it's not in the denominator, the sine squared, what's it going to do? We have something like a 1 over x or a constant over x maybe. And we can deal with constants over x because it's the same as 1 over x just multiplied. We can pull out that constant from the integral. So if we can bound sine squared, bound the function in the numerator by a constant, it'll help us. And I know that sine squared is always positive between 0 and 1. Meaning that this integral is going to be less than or equal to pi over 2 to infinity from 1 to x dx. So what's that mean? Any takers? I'll put it in orange.
I squeeze theorem.
Gotta be careful with that one.
Not squeeze theorem?
Eh,
Yeah, between 0 and 1.
Squeeze theorems often are used here, but with sines and cosines, but not for this particular problem. If we're trying to do a direct comparison theorem, what happens to 1 over x?
Sine squared x is less than 1. I don't know.
Oh,
Sine-
the max sine squared x can be as 1, so we use that.
So
Right.
this guy converges, but you gotta be careful. Test is inconclusive. Why? Here I have something. Oh wait, why did I write converges? Diverges. Right?
Well,
Or 1
that's-
over x to the
Oh,
1
that makes
diverges.
sense.
But our test is inconclusive because this one goes off to infinity. I have something that's less than infinity. What's that mean? It could be
You
a
don't know where
smaller,
it lies between
Yeah.
there and infinity. So
could be a smaller infinity, or it could be a finite value. So we don't know. And then, of course, what would the other side be if we wanted to bound it to the left? Well, we'd bound it by 0 over x. So I know something is bigger than 0, but less than infinity. What's that tell us? Nothing, really. Could be anything. So careful with stuff like this. Maybe we'll do some more examples tomorrow because it's easy to misthink some of these comparisons. And so sometimes with this one, no direct comparison is going to work. All right, so that's it for today. Maybe we'll take a look at some more of these examples. I think you guys have quite a few of these on your homework. So maybe we could either take a look at some of those or take a look at WebAssign if we want to get a head start on some of those. to pull some examples of just doing quick comparisons and practicing looking at functions and trying to understand rates of growth, rates of decay, and things we can compare functions to when we're taking compositions and sums and differences of functions.